Okay, let's start. In this lecture, we're going to discuss about the normal forms of saddle node bifurcation. So in the saddle node bifurcation, we have seen one example which is in the following manner. The system has been described like this: r minus x square, or I think plus x square. Okay, so if it's in this form, then we will have a saddle node bifurcation. Even if it is r minus x square, even then it will have a saddle node bifurcation that you could verify. Okay, now the claim is, for any system, if the saddle node bifurcation happens, then near the region where the bifurcation happens, the system will look like this. Locally, the system, or in the small region, the system will look like this. Okay, so that's the claim. Okay, so let's see how to make sure. How to prove that claim. First, I am going to use an example, the example which we have seen already, which is x dot is equal to r minus x minus e to the power of minus x. So this is an example we have seen, and we also observed that a saddle node bifurcation is happening for this system at some particular r value, right? So now but this system doesn't look like this one. Okay, so what are we going to do? What we're going to do is the following: we are going to keep these first two terms as it is, okay, and we are going to expand this term. Okay, if we expand this term, what do we get? A Taylor expansion. Okay, so 1 minus x plus x square by 2 plus not plus, minus, we will get minus x cube by 3 factorial plus dot dot dot. Okay, so this is what I will get. Okay, so for this system, what is the x star value, which means the equilibrium point? The equilibrium point at bifurcation was 0, right? 0 at bifurcation, right? So therefore, what I'm going to do is, if x is very near to the bifurcation point, which is x star equal to 0, then I could ignore the higher order terms, and if I ignore the higher order terms, I will get it in this manner: r minus 1. Okay, so this x and this x will get cancelled, then minus x square by 2 plus the higher order terms, the order of x cube, right? So this is what I get, and I could ignore this higher order terms, and if I ignore this and if I see this term, this exactly, not exactly, but this somehow looks like this. The only thing is, we have to scale this x. If I scale it, then I will have it in this form, right? So yeah, now we could see it for this example, right? But is it a common thing? The answer is yes, and that's what we're going to see further. But before that, I will also show you something. I will show this answer. Okay, I'll show this answer graphically that it is true. So claim is this is the form, right? This is the form, and if I plot that, I will get this parabola, and if I change this r value, then suddenly 2 fixed points will appear, right? And if I decrease it, then 2 fixed points will disappear and there won't be any fixed point, and at a critical point there will be only one fixed point, right? So this is that fixed point. Okay, now let's see. So that's for this one. Now let's plot this function. Okay, how does it look if I plot this function? Let me hide this, and then let me start with this one. Okay, so this is the curve I'm getting. Okay, and if I plot it, yes, suddenly I'm getting 2 fixed points, right? So this is a saddle node bifurcation, but does it look like so now the claim is locally it will look like this, right? This particular equation will locally, when the bifurcation happens, in the region when the bifurcation happens, where the bifurcation happens, the function will look like this, right? So now let's plot that function. So this is that function, okay, which looks like a parabola, right? And now the bifurcation happens when x is equal to 0, right? And at that region, let's plot the actual function as well. And if I plot, see, very locally, this curve, this green one, which is the actual function, looks like a parabola, right? So that's what the claim is. So locally we will have, if the system is having a saddle node bifurcation, then locally we will see that system behaves in this manner. Okay, fine. Let's show that this is true for not just for this function but in general. Okay, let's take a function x dot which is equal to f of, now it's going to be a function of not just x but also a function of r, the control parameter. Okay, fine. Now I am interested to know the behavior of this function near to the bifurcation, right? So bifurcation happens at x is equal to x star and r is equal to r critical, right? So now what I'm going to do is I'm going to do a Taylor expansion of this function with respect to this point. Okay, so in that case, what do I get? F of r critical comma x star, right, plus x minus x star into, let me write f comma x, where f comma x represents dou f by dou x. Okay, and this I am evaluating at this point. Okay, x star and RC. Okay, x star and RC plus R minus RC, that's the deviation from of R from RC, into f of f comma R, right, and I'm evaluating at the same point. Okay, so just leave it as it is. Then plus half x minus x star square dou square f by dou x square. So I'm going to put x and I am evaluating it the same these points. Okay, and I will have some higher order terms. Okay, now in a very near to this region, let's say I'm ignoring these higher order terms, and what do I get? I will get it in the following. I'll get the following function, which is a into r minus rc. Okay, where a is nothing but this one. Okay, plus b into x minus x star square, where b is half into this function. Okay, what about this term and this term? This term will be 0 because x star is a fixed point, and therefore this term will go to 0. Okay, fine. But what about this term? Even this term will go to 0. The reason is we have evaluated this f comma dou f by dou x at x star and rc, r critical, right? At r critical, this function will also vanish. So the time it vanishes, if you see, when the bifurcation happens, then at that time the system will have the fixed point neither stable nor unstable. It will be half stable, right? So when the system is having a half stable, then the linear term will get vanished, and if the linear term, this is the linear term, and the linear term will get vanished. Okay, therefore finally I will have my x dot in this form. Okay, and now let's introduce a variable u, okay, which is equal to x minus x star. So basically it's the deviation of x from x star. Okay, and let me use this one over here. What do I get? I'll get u dot, which is equal to this constant, whatever it could be. Okay, let me call that as capital R. Okay, so this is what the capital R is, plus a constant, a scaling factor, okay, u square, right? So we have got this, right? So we have got that in general, if a saddle node bifurcation happens, then we will have this form, okay. So therefore this is known as a normal form for saddle node bifurcation. In the next video we will see the other bifurcations. Thank you.